Good to go. Okay, so let's get started on reverse engineering and disassemblers. First things first, the disclaimer. You can do some bad stuff with reverse engineering, obviously, so don't do that. Please do not reverse engineer Lockdown Browser or the Get app or anything like that. Okay? If you do, and you get caught, we'll make fun of you publicly. So why would we want to reverse engineer something? So perhaps we have lost the source code, or there is no source code for what we have acquired. We want to make sure that we're not downloading any malware or the good old-fashioned Bitcoin miners. Or we want to do some modding in a game like Skyrim, The Witcher, or in the source engine. So to start reverse engineering, you need to know a lot about low-level you have a lot of low-level understanding for computers. You need to know a lot about memory, which has to do with stack. You have to know about registers, assembly. You have to know opcode instructions. And if you know C and C++, you'll have a better time adapting to that environment because you're going back in time. You're going to 1940 where you had punch cards sticking instructions into a machine. That's how hard, I guess you could say, it is to reverse engineer. So everybody knows that computers read ones and zeros. That's halfway true. Instead of reading just the 1 and 0, they read the bytes that are aligned, which are mapped to instructions like load, pop, push, and move. So reverse engineers can manipulate these bytes for their own benefit, for good or bad purposes. So to go from an executable, like a game or an install executable, you have to disassemble it and go backwards. If you write in, let's say, C, you compile it and then it goes into the machine code and then the executable. You want to go backwards, which is slightly harder than compiling. So you want to disassemble, and you have disassemblers like IDA Pro, which has been doing this since the 90s. In my opinion, they're the best because they've been doing this forever. And that's why they cost several $1,000s to get a license. There's Ghidra, which is fairly new. It's the NSA's open source Java disassembler and decompiler. It's made a lot of headway the past couple of years. Its decompiler is really good. It's on par. Well, not really on par with IDA, but it's better than some trash. There's Radar, which is also open source. People like Radar because you can run it in a terminal, but it's got a steep learning curve. There's a lot of fancy business you have to understand to really get to use it. If you take Intro to Cybersecurity, CSC 442, you'll have to use, they'll teach you Radar. You don't have to use it. I didn't. I used IDA and I smashed the challenges, but they will teach you Radar and you're going to go, what the hell am I looking at? That's okay, because it's got a really steep learning curve. There's also Binary Ninja. It's like $90 for a license, and I've heard a lot of good things from them. They're like really in with the community. The forum is really active. I have a friend that uses Binary Ninja. But the purpose of these disassemblers is to convert the executable back into something that you can kind of interpret, right? So down here we have IDA and then Ghidra. Over here is Radar, or Radare, I don't know how you pronounce it. If you are in the 130 series and you saw this picture, you would go, what the hell am I looking at? But that's okay. That's why you're here. And that's really hard to understand assembly code. Fortunately, we have decompilers. So we go another step above. We go from machine code to assembly, and then we go back up to a higher level language like C with a decompiler. They're not always perfect because reverse engineering is not always perfect. If it was, it wouldn't be that hard. So if you've taken the 130 series, you've probably seen a graph like this, where you go from machine language, or you go from, your visual languages like Python down to C, which is down to assembly in the machine, and then it makes system calls to hardware. We are, let me get a pen. We are here at machine languages, and we want to go up. We're going to disassemble up to assembly language. And if you have a decompiler, you can go from the assembly language up to a higher level language like Fortran, C, Pascal, COBOL, BASIC. And from there, we can understand, hey, this is what this thing is doing. We can go, oh, that's malware or something like that. Or we can have our own payload. Way back in the fall quarter, we did Shelter. It was a system or a program that put a payload into the machine languages, into the machine language of the executable, or of an and executable. And so to make Shelter, whoever brilliant soul did that, they had to know a lot about assembly and other various high-level languages. So now that we kind of have the basics, let's reverse engineer some stuff. If I can get out of this. So I have compiled 2 handy-dandy binaries. We're going to start with wait. We're going to run this. And it's going to give us a password in 10,000 seconds. I don't want to wait that long, and I don't think you can do either. So we're going to disassemble this binary and hopefully give ourselves an easier time. So I'm going to pull up IDA, and I'm also going to pull up Ghidra so we can draw some comparisons. Load that up. And we're going to pull up Ghidra. I prefer IDA, Ghidra, although it is good for being free, it is kind of slow. We're going to go to Code Viewer. And drop this here. Okay, cool. I think because I already have one in there. Hold up. Destination file name already exists. Great. What if I just make a new project? This is why I like IDA, because I can just drag and drop it and it's already there. So let's get out of this. I'm going to make new project. Oops. Unshared. Name. Wait to finish. And it is awesome. Wow. Whatever. Okay. Active project wait to. Try this again. This is desktop base. All right. Man, that was complicated. So now it's going to analyze this binary file. Yes, please analyze. And it's going to find our main function. Everything is a C programs. Everything starts at main. I think it's still analyzing. Find main. Yep, we're at main. Back to IDA. We're also at main. Okay, now we can compare. First things first, I like opcode bytes. They're easy. I want to patch something. So looking at this, you're going to say, what am I looking at? That's okay. Well, we have a decompiler. So let me get rid of these tabs. We'll decompile this, and then I will decompile on Ghidra. So we'll look at IDA first. So it looks kind of silly because it's not a complete perfect one-to-one of the actual source code that went in. But you can kind of deduce what you're looking at. So for I equals 10,000, I not equal to 0, minus minus I. This is your standard output. Password will be given in I seconds, and then it will sleep for 1 second. And then after that, I'll give the password. Just pretend that doesn't exist, pretend that's not there. And in Ghidra, it's slightly different. Instead of making it a for loop, it's a while loop, but it's basically the same thing. For sanity, we can rename things because you don't want to just look at local or v1, v2. But if the decompiler, at a basic function like this, they're pretty similar, but a more complex function is, I believe IDA has the upper hand and will for a long time. But our problem here that we want to circumvent is that I is equal to 10,000. We don't want I to equal 10,000. We want it to be 0 or 1. So we have to look at the bytes and say, hey, let's change this 10,000 to something else. I'm going to hex this because bytes are stored in hex. So we look back over at the disassembly. We went to look for a, well, 2710. There it is, 2710 over on the right. But to change it, we have to look at the left, which is our bytes. We see 1027, which is actually our 10,000. So it's backwards. That's okay because under many architectures, this is called NDNS with an E. And this is Intel x86. It's big Indian, so that means it's backwards. So we want to change this. We'll change it to 1. So to change these bytes, once you go to Edit, Patch Program, Change Byte, we start at 48. We want to go all the way over here. We're backwards. So 27 becomes 0, and then the 10 becomes 01. So now we are moving with this into register, which is the base pointer right here, register RBP. And then we can decompile it again. And then now it will say I is equal to 1. I is not equal to 0, minus I. So now we have changed it on the database, the IDA database. Now we want to place this into the executable that we dragged over here. So we go back to patch program, apply patches to input file. Okay, let's apply the patches. Let's see if it worked. Let's run it again. Wait that out. Pass will be getting in 1 second. Please let me in. 1, 2, 3. Ta-da, we did it. We have patched over some bytes to get the output that we want. So the thing I said to ignore, which is give password, yep, that was it right there. It's not going to be like that. Hopefully, if you have somebody that's giving you a password, it is encrypted or obfuscated somehow. But if we look over here at the disassembly, take a sip of water. Whenever you make a string in a compiled language, most compiled languages, your hello worlds, your please let me ins, it replaces what you're trying to send with an address, which is in this case renamed to this please let me in. And the string itself is sent to what's called the data section. There are different sections and segments of a program. You know, like headers, you can put a payload into a header of a video file. I read on Discord, or I read on Twitter earlier today, that Discord has a 0-day right now, where there is a video MP4 that you can play, and the header is manipulated to crash your computer and also execute shellcode. So if anyone sends you a video, don't watch it. That's my recommendation. But back to this. So it sends these strings to what's called the data section. In this case, it's a Linux compile, so it's row data. And you'll see a bunch of bytes over here. Password will be given in, we have seconds, and then the password itself. These bytes over here are what's called, well, if you look at an ASCII chart, you'll see that these bytes are mapped to letters, characters. C strings are UTF-8 compliant. That means that if you have a string, it will go all the way through the string and it will pick each character and then print it or send it somewhere until it reaches a null byte or 0. So seconds, this is space, seconds, and then 0 to terminate the string. We can manipulate these bytes if you wanted to. We can edit, patch program. Actually, let's patch it anyways. I don't know ASCII by heart, but if I change this to 52, it'll be like R. Yeah, R. So now it's R, let me in, and we can patch program over our input file, and run it again, and now it's this. That's for fun, but you can change anything in the binary. That's how malicious executables are created. As long as the header is intact, you can still run the program until it's like false. So that was some basic patching. We're going to not save this. Also going to save my RAM and hop out of Ghidra. So now we have another file, which is trash.out, which we can run. It's asking us for a password. So let's try the password that we got earlier. Please let me in. 1, 2, 3. That's wrong. You have 2 tries remaining. So all right, let's try something else. 1, 2, 3. 3, 2, 1. And then we're out of tries, and then it caught us. The NSA got to us. But so now what we want to do here is find a way to get past the password input. So back here, trash.out. And that's done. Back again to opcode bytes. Those are our best friends. So we have here, we have our prints. Please insert a password. We're going to decompile this. So right here, these are all prints. C out takes our input as C in. I equal to 3, I equal to 0, minus I, same stuff. If you look at it long enough, you start to figure things out. Our password's the same. That looks like, hey, maybe the password is in here, right? True, but it's obfuscated to the point where you probably don't want to try to de-obfuscate it. You could if you tried really, really hard, but that would be a lot of effort compared to something else you could try. So what you're seeing right here, that there's a basic standard string, and it's doing some obfuscation to get the password. And then it's going to compare the input string with the new string, which is the password, and which is true or false. And then it returns it. Also, the size, it's a 64-bit integer. Not really. We can change that type to, oops. We can change that to bool to save ourselves a headache. So now it's bool, fast call, our password's the same. If they're the same, returns 1, not returns 0. You get the gist. So we're going to go back to where it says this. So we don't know the password. We can't feasibly find the password. How do we get to this function, which is yay, assuming that these passwords are the same? How do we get to here as easily as possible? We have a couple of options. Option 1, we could make this true no matter what. Option 2, maybe we could just call this function regardless somewhere up here. Or we could maybe, if we could just go right here and then click backspace. But we can't do that. We have to patch over the bytes, right? So the easiest option, in my opinion, is to just go over here and then patch over this to where there's not even an if statement, not even an if statement. So we check over this assembly, and this is where you need to understand a little bit about opcode instructions and registers and what happens, jumps. So it's right here. It's these 2 lines. So it calls the function. If you can see that our password is the same, and then the return value is stored into register EBX, and then it calls some other stuff. And then we have the test code, which test stands for and, so bitwise and then the BL is EBX. So if we went a step up from test, we would go, oh yeah, this is the source for the code. We're going to go test is equal to BL and BL. So if BL is 1, 1 and 1, which is equal to 1, right? But if BL is 0, be 0 and 0, which is equal to 0. Basically, it's true or false, to make a long story short. and then the test command throws up something into the air, throws up a 1 or a 0, and then I forget the terminology, but this command is jump if 0. JZ is jump if 0. So if BL is 0, it's going to jump to this location, which it skips over all here, which it calls yay. It jumps around. It's going to jump over here and says, no, password is wrong, and then continue all the way back to the start and continue the loop for 2 more tries. So we want to just take this, and if we could press backspace or delete, but we can't. We need to get these bytes and then get rid of them. Fortunately for us, there's an opcode instruction called NOP, where it is akin to hitting the delete button on your keyboard. It's not far back enough. So you go to edit, patch program, change bytes. You start at 84. Opcode for NOP is 90 hex. We change these 4 to NOP. Now, these are nothing, NOP nothing. Now, we can skip over the trash that was prohibiting us from reaching the function we want called. If we decompile this again, IDA is smart enough to optimize out the stuff we don't need to look at. So now what it does is it takes the input. It's still going to call this. We could knock that out if we wanted to, but it's not really a big deal. But regardless, no matter what happens, it's going to call the function that we are looking for. So I'm going to apply the patches to our input file, and then we're going to run it. Trash that out. It's going to ask for our password. Doesn't matter what we put in there. Enter, and then we're into Area 51. We've bypassed the security, and we are free to do whatever we want. Yeah, that's basically it for introduction. There's a lot more you can do. You can make your own jumps, make your own functions if you want to, if you try hard enough. Just the main problem you'll have is that you don't have a lot of bytes to work with. That's why, that's why in many games it's a runtime modification. The binary is loaded up into RAM, and then you have another program running alongside it, another library, a shared object that finds the module in RAM and then overwrites the memory at runtime. That's how it is for the source engine. Damn. That's how it is for the source engine. That's how they do it. But yep, that's a basic introduction to looking at disassembly and manipulating it for your own benefit. Are there any questions?
Thanks, man. That was really cool.
Sure thing, man. No questions, comments, concerns? Chat. Yeah, I drink water. Thanks, man. All right, well, we'll stop recording.